we start the next topic of derivative, which is derivative of parametric functions. Parametric function means if the given function are in the parametric forms, which is in form of parameters. Suppose that if we observe that differentiable function is in the form of y is equals to f of x, but in the parametric form the function given in is the different parameters forms. Here x is equals to f of t and y is equals to g of t. Then we can say here function x is equals to and function y is equals to x and y is both functions. Both functions are in the form of f of t and g of t. It means that here t is a parameter. Hence we can say that x is equals to f of t and y is equals to g of t are both functions in the parametric form, which parameter is t. Here we learn first theorem of the parametric function is if function x is equals to f of t and y is equals to g of t are a differentiable function of t. T is a parameter and function is differentiable at t, so that y is differentiable function of x and dx upon dt is not equals to 0, then we have to prove that dy upon dx is equals to dy by dt upon dx by dt, such that dt cancel, dy upon dx as it is. The proof of this parametric function is, here we know that by the given condition two parametric function is which is in the form of x is equals to f of t and y is equals to g of t. Here x is equals to f of t and y is equals to g of t. There will be a small increment value, which is if function is dx, then its small increment is del x. Function is dy, is small increment is del y, such that here the parametric form, which is in the form of t is a parameter, the small increment in the value of t say that del t. Similarly, small increment of x say del x and the small increments of y say del y. As del t, del x, del y are small increment in t, x and y respectively, such that del of t is not equals to 0 and del of x is not equals to 0. Consider incremental ratio del y upon del x and note that del x tends to 0 and del t tends to 0. The limit of del t and del x tends to 0. That is, we can write it del y upon del x is del y by del t upon del x by del t. Since del x by del t is not equals to 0, because when denominator becomes 0, then the value of this function, whole function is infinity. And the value of infinity in mathematics does not exist. Hence, it is clear that del x upon del t is not equals to 0. The value of del x upon del t is not 0. Taking the limit both sides, if we take the limit both sides, such as del t tends to 0 on both sides, we can write del x tends to 0, del y upon del x is equal to limit del t tends to 0, del y by del t upon del x by del t. If we separate this limit both numerator and denominator, we can write del x tends to 0, del y by del x, limit del t tends to 0, del y by del t upon limit del t tends to 0, del x by del t. Now, x and y are differentiable function of t. We have limit del t tends to 0, del x by del t is equals to dx by dt, because del x by dt is a very small increment of dx and dt. If we put the limit of this limit del t, then we can write limit del t tends to 0, del x upon del t is equals to dx by dt. Now we again write limit del t tends to 0, del y by del t is equals to dy by dt, because del y by del t is a small increment of dy by dt, and if we put this limit del t tends to 0 in del y by del t, then we can write the value of limit del t tends to 0, del y by del t exactly dy by dt. It gives we equation number second. This equation number first, if we put from equation 1 and 2, we can write limit del x tends to 0, del y upon del x is equals to dy upon dt upon dx by dt. Equation number 3. We can write right hand side of the equation 3 exists. Hence, left hand side by using equation number 3 also exists. And finally, we can write finite limit del x tends to 0, del y upon del x is equals to dy by dx. Hence, thus the equation 3 become, we can write del y by del x limit del x tends to 0, del y by del x is dy by dx. We can write, if we put this value of limit del x tends to 0, del y by dx, dy by dx is equation 3, we can write dy upon dx is equals to dy by dt upon dx by dt, hence proved, which is here del dx upon dt is not equals to 0. By this condition, by using this process, we can prove that dy upon dx is equals to dy by dt upon dx by dt, which is also called as definition of parametric functions. By using this definition of parametric function, which is dy by dx is equals to dy by dt upon dx by dt, dy by dt upon dx by dt, we can solve the following example which are as given. Now we start the question number first, which is in the find dy by dx is first example, x is equals to a raised to the power 4 and y is equals to 2at square. Now here we have to find dy upon dx, the given function which is in the form of parametric functions. Now x is equals to 8 raised to the power 4, y is equals to 2at raised square. Here t is a parameter, hence we can differentiate with respect to both x and y. Now we first take differentiate. Given that x is equals to 8t raised to the power 4 and y is equals to 2at square. If we differentiate with respect to t, both x and y, we can write it derivative with respect to t of x. Here a is constant function, derivative of t raised to the power 4. Here again we can write dy upon dt. Here twice a is constant, we can take a derivative of t square with respect to t. We know that the derivative of t raised to the power 4, which is 4t raised to the power 3. Hence we can write dx upon dt is equals to 4at cube, equation number 1. Now again here twice a as it is, we can write the derivative of t square, which is 2t, 2 into 2 is 4at. This is a required derivative of y, which is dy by dt, equation number 2. But we have to find dy by dx. If we have to find the value of dy by dx, first we take by using definition of parametric function. Definition of parametric function. We know that the definition of parametric function is dy by dx is equals to dy by dt upon dx by dt. Here dy by dt is 4at and dx by dt is equals to 4at cube. Now we can write 4a cancel. Here t upon t cube is equals to, if t is cancelled, we get t square. 1 upon t square means a required value which is dy by dx is 1 upon t square when x is equals to a raised to the power 8 t raised to the power 4 and y is equals to 2at square. Write down. Now the given function also is in the parametric form. Here x is equals to t minus root t, y is equals to t plus root t. Again here t is a parameter. First, if we have to find the derivative dy by dx with respect to x, then we first take a given functions given that which is x is equals to t minus root t and y is equals to t plus under root t. Here t is a parameter. If we differentiate both with respect to t, x and y, we can write derivative with respect to is x is equals to derivative of t minus derivative of under root t. Derivative of t is 1 and derivative of 1 by root 2 root t is 1 by root t. Here we can write 2 root t minus 1 upon 2 root t, which is the value of dx by dt, equation number first. Similarly, we can find a derivative of y with respect to t, which means dy by dt. Here, if we take the derivative with respect to t of y, we can write a derivative of t plus a derivative of under root t. derivative of t is 1 plus derivative of root t is 1 upon 2 root t. If we take the cross product of both, we can write 2 root t plus 1 upon 2 root t, which is value of dy by dt, equation number 2. We know that by the definition of parametric function, we can write dy upon dx is equals to dy by dt upon dx by dt. Here the value of dy by dt is 2 under root t plus 1 upon 2 root t upon 2 root t minus 1 upon 2 root t. Here 2 root t cancel. We can write 2 under root t plus 1 upon 2 under root t minus 1, which is the required value of dy by dx. Example number 3 again, which is in a parametric form. Here parameter also is t. First we take, if we have to find dy by dx, first we take given a function which is x is equals to cos of log t and y is equals to log of cos t. If we have to find dy by dx by using definition of parametric function, then first we find dy by dt, again dx by dt, and by using the definition of parametric function, we can find dy upon dx is equals to dy by dt upon dx by dt. First, if we differentiate with respect to t, both x and y, we can write derivative of x dy by dt, which is derivative of t cos of log of t. We know that the derivative of cos, which is minus sign, hence we can write minus sign of log t, and we take again a derivative of log t. Derivative of log t is 1 by t, hence we can write minus sign of log of t upon t, which is dx upon dt, equation number first. After that, if we differentiate with respect to t, which can get dy upon dt, we get a derivative of log of cos of t. Log of cos of t. The derivative of log, which can write we 1 upon cos t, and we take again a derivative of cos t. We know that the derivative of cos, which is minus sign, hence we can write minus sin t upon cos t. We can write it minus tan t, which is the value of dy by dt, equation number 2. We have to find dy by dx by the definition of parametric function. We can write dy upon dx is equals to dy by dt upon dx by dt. Again we know that the value of dy by dt, which dy upon dx is equals to dy by dt is minus tan t upon dx by dt is minus sin of log of t upon t. Hence, if we take this t on numerator, we can write minus t tan t upon minus sin of log t. Here minus minus cancel. We can write dy upon dx is equals to t tan t upon sin of log t, which is a required derivative of dy by dx. Now the next example number 4, which is also in parametric form. Here given that theta is a parameter. When we use the definition of parametric function, which is also in form of theta. Now first we can write given function, given that x is equals to a in bracket theta plus sin theta and y is equals to a in bracket 1 minus cos theta. If we differentiate with respect to theta, then we can both x and y, we can write dx upon d theta is equals to, here a is constant, we can write d upon d theta in bracket theta plus sin theta. Again, if we take derivative with respect to theta, we can write dy upon theta in bracket derivative of 1 minus cos theta. Now here a is constant, derivative of theta which is 1 plus derivative of sin theta is cos theta. Again we can write a into derivative of 1 is 0, derivative of cos theta is minus sin theta. Now we can write a into 1 plus of cos theta is equals to minus plus we can write a sin theta. We get here dx upon d theta is equals to a in bracket 1 plus cos theta, and dy by d theta is equals to a into sin theta. By the definition of parametric function, we can write dy upon dx is equals to dy upon d theta upon dx upon d theta. Similarly, if we put the value of dy by d theta a sin theta and dx by theta is a into 1 plus cos theta, here a is cancelled, we can write sin theta upon 1 plus cos theta. If you have to solve again this, we can write dy upon dx is equals to sin theta means 2 sin of theta by 2 into cos of theta by 2 upon this 1 plus cos theta is 2 cos square theta by 2. 2 to cancel, square cos theta by cancel. Here we can write sin of theta by 2 upon cos of theta by 2, which is value of dy by dx is equals to tan of theta by 2, which is a required derivative dy upon dx. Or you can write finally answer sin theta upon 1 plus cos theta. Next function which is also in parametric form. Here x is equals to under root of 1 minus t square and y is equals to sin inverse of t. Here t is parameter. First we take given function, given that x is equals to under root of 1 minus t square and y is equals to sin inverse of t. If we differentiate with respect to t both x and y, we can write derivative of tx, derivative of under root of 1 minus t square. Again we can write dy by dt is equals to derivative of sin inverse of t. This is a function which is in the form of under root. We can write it 1 upon 2 under root of 1 minus t square, and we take again a derivative of 1 minus t square. We know that here derivative of 1 is 0 minus derivative of t square is 2t. We can write minus 2t upon 2 under root of 1 minus t square. Here 2 to cancel, we can write minus t upon under root of 1 minus t square, which is a value of dx by dt, equation number first. Now again we can take a derivative of sin inverse t, which is 1 upon under root of 1 minus t square, which is a derivative of dy upon dt, equation number 2. By the definition of parametric function, we can write dy upon dx is equals to dy by dt upon dx by dt. Here the value of dy by dt is 1 upon under root of 1 minus t square, and the value of dx by dt is minus t upon under root of 1 minus t square. Here 1 minus t square under root 1 minus t square cancel, minus 1 upon t, which is a required derivative, and final derivative, the value of dy by dx is equals to minus 1 upon t. Next question, which is also same question. Here we have to find dy by dx. Given function is x is equals to sec square theta, y is equals to tan square theta, but we have to find the exact or definite value at theta is equals to pi by 3. If we have to find dy by dx, first we take given function x is equals to sec square theta and y is equals to tan cube theta. If we differentiate with respect to theta, then we can write dx upon d theta is equals to derivative with respect to theta sec of theta bracket square. Again we can apply here dy upon d theta is equals to derivative with respect to theta tan of theta whole bracket cube. We know that Here we apply derivative which is x raised to the power n. Again here x raised to the power n, we can write derivative of x raised to the power n is 2 sec theta. We can take again the derivative of sec theta. Here 2 sec theta as it is, and derivative of sec theta is sec theta into tan theta. Hence we can write dx upon d theta is equals to 2 sec square theta into tan theta, which is equation number 1. Now again we apply here 3 tan square theta into again the derivative of tan theta. We know that derivative of tan theta is sec square theta. Hence 3 tan square theta and the derivative of tan square theta is sec square theta, which is the value of dy by d theta, equation number 2. We know that definition of parametric function, which is dy upon dx is equals to dy upon d theta upon dx upon d theta. Here the value of dy by d theta is 3 tan square theta into sec square theta upon 2 sec square theta into tan theta. Here sec square theta cancel, tan square tan theta cancel. We can write it 3 by 2 into tan theta. But we have to find value of dy by dx as theta is equals to pi by 3. Hence we can write dy upon dx at theta is equals to pi by 3 is equals to theta into tan of pi by 3. The value of tan of pi by 3 is under root 3. Hence we can write 3 root 3 upon 2, which is the required value of dy by dx at theta is equals to pi by 3. Next example which is in the question number 2 is x is equals to t plus 1 by 2, y is equals to 1 by t square, and we have to find the value of dy by dx at is t is equals to 1 by 2. First we take given function which is given that x is equals to t plus 1 by 3 and y is equals to 1 upon t square. If we differentiate with respect to t both x and y, we can write dx upon dt is equals to derivative with respect to t is t plus 1 by t. Derivative of y with respect to t is derivative with respect to t. We can write dt square is t raised to the power minus 2. Derivative of t is 1 and derivative of 1 by t square, 1 by t is minus 1 upon t square. Hence we can write it 1 minus 1 upon t square. Derivative of t raised to the power minus 2 is minus 2 into t raised to the power minus 2 minus 1, which is minus 2 raised to the power 3 minus 2 upon t cube. Similarly, we can write here t square into 1, t square minus 1 upon t square, which is value of dx by dt, which is the value of dy by dt. By definition of parametric function, we can write dy upon dx is equals to dy by dt upon dx by dt. The value of dy by dt is minus 2 upon t cube. Here we can write the value of dx by dt is t square minus 1 upon t square. If we write minus 2 upon t cube into t square upon t square minus 1. Here t square cancel, we can write minus 2 upon t into 1 upon t square minus 1 is minus 2 upon t into t square minus 1, which is the value of dy by dx. But we have to find the value of dy by dx at t is equals to 1 by 2. dy by dx is equals to dy by dx at x t is equals to 1 by 2. Here t value of t is 1 by 2 minus 2 upon 1 by 2 into square of 1 by 2 is 1 by 4 minus 1. Here if we take minus 2 numerator, we can write minus 4 upon 1 into 1 minus 4 upon 4. Here this 4 we can write it 4 cancel, 1 minus 4 is minus 3, minus 1 upon minus 3, which is a value of 1 by 3. Required value dy by dx is 1 by 3. Sorry, This 4 is not cancelled. We can write here minus 2 into 2 upon 1 by 4. Cross product of 1 minus 4 upon 4. Minus 4, this if we take this minus sign, numerator we can write minus 4 into 4 upon minus 3. Minus 16 upon minus 3, which is the required value of dy by dx as t is equals to 1 by 2 is 16 upon 3. Example number 3 is x is equals to 3 cos t minus 2 cos cube t and y is equals to 3 sin t minus 2 sin cube t at t is equals to pi by 6. Here we have to find dy by dx at t is equals to pi by 6. It means that it is clear that we get the definite value of dy by dx. First, if we have to find the dy by dx and the given function is parametric functions or parametric form and t is a parameter, then first we differentiate x and y both with respect to t. If we differentiate x, we can write derivative with respect to x. Here 3 cos t, derivative with respect to t, d upon dt of x is equals to derivative with respect to t 3 cos t minus 2 cos cube t. Again we can write derivative of y, which is dy upon dt is equals to derivative of 3 sin t minus 2 sin cube t. Now here 3 is constant function and the derivative of cos t is minus sin t. Again minus 2 is constant function. By using the derivative of x raised to the power n, we can write derivative of cos cube t is 2 cos square t and we take again the derivative of cos t. Here again we can write 3 into minus 3 sin t minus 2 into 2 is 4 cos square t and the derivative of cos t is minus sin t. We can write minus plus sin t. Hence it is a value of, if we take sin t common both, we can write sin t into minus 3 plus 4 cos square t, which is a value of dx by dt. After that, if we take a dy by dt, we can write a derivative of 3 sin t, 3 is constant, derivative of sin t cos t, minus 2 into derivative of sin cube t is 3 sin square t and we take again the derivative of sin t. Here again 3 cos t as it is, 3 into 2 is 6 sin square t and the derivative of sin t, which is cos t. If we take cos t common both, we can write cos t into 3 minus 6 sin square t, which is a value of dy by dt. By using the definition of parametric function, we can write dy upon dx is equals to dy by dt upon dx by dt. Here the value of dy by dt is cos t into 3 minus 2 sin square t upon sin 2 into minus 3 plus 4 cos square t. If we substitute the value of t, here derivative of cos cube t is 3 cos square t into again derivative of cos t. We can write here 3 into 2 6, which means that 6 cos square t. Here again we can write 6 cos square t, 6 cos square t. If we take 3 common from these two functions, we can write 3 cos t into 1 minus 2 sin square t upon, again if we take 3 common, we can write 3 sin t into there 2 cos square t minus 1. We know that 1 minus sin square t is a form of Hence we can write dy upon dx is equals to 3 cos 3 cancel. We can write cos t upon sin t as it is. 1 minus 2 sin square t means cos 2t. Again 2 cos square t minus 1 is again the formula of cos 2t. We can get cos 2t cancel. Cos t upon sin t we can write cot t. Here we have to find derivative dy upon dx at t is equals to pi by 6. Here we have to find the value of cot of pi by 6, and we know that the value of cot of pi by 6 is under root 3, which is a required derivative of the given function dy upon dx. Next example, which is question number 3, is if x square plus y square is equals to t plus 1 by 2 t, and x raised to the power 4 plus y raised to the power 4 is equals to t square plus 1 upon t square. Here we have to prove that dx cube y into dy by dx is equals to 1. Here parameter t is totally removed from these functions. The given function is in the form of implicit functions. If we have to find a derivative which is dy by dx, then first we take a derivative of x with respect to parameter t, again derivative of with respect to x this function with respect to parameter t. Now by the given condition we know that given that x raised to the power 4 plus y raised to the power 4 is equals to t square plus 1 upon t square, which is equation number 1. Now we can again write given that x raised to the power 4 plus y raised to the power 4 is equals to t square plus 1 upon t square, equation number 1. Secondly, again given that x square plus y square is equals to t plus 1 by t, equation number 2. If we square these both sides, squaring both sides, we can write x square plus y square whole bracket square is equals to t plus 1 by t whole bracket square. Squaring both side, equation 2. Here the square, if we use a plus b bracket square, then we can write x square of square, which is x raised to the power 4 plus product of both n is double 2 into x square y square plus y raised to the power 4 is equals to square of the first element t square plus product of both n is double 2t into 1 by t plus 1 upon t square. Here x raised to the power 4 plus 2x square y square plus y raised to the power 4 is equals to, here t is cancelled, t square plus 1 upon t square plus 2 as it is. If we substitute the value of t square plus 1 upon t square is x raised to the power 4 plus y raised to the power 4, we can write x raised to the power 4 plus 2x square y square plus y raised to the power 4 is equals to the value of 1 plus t square plus 1 upon t square is x raised to the power 4 plus y raised to the power 4 plus 2. This value we take from equation 1. Now here x raised to the power 4, x raised to the power 4, y raised to the power 4, y raised to the power 4 cancel. We get 2x square y square is equals to 2. Again we can get cancel 2, we can write x square into y square is equals to 1. We have to prove that the derivative x cube y into dy by dx is equals to 1. If we differentiate given function with respect to x, then we can write u into v formula, x square into derivative of y square plus y square into again the derivative of x square, and the derivative of constant function is 0. Now here x square as it is, and the derivative of y square is 2y into dy upon dx. Again plus y square as it is, derivative of x square is 2x is equals to 0. Here we can write 2x square y into dy by dx is equals to 2xy square, plus 2xy square is equals to 0. If we shift this 2xy square right side, we can write 2x square y into dy by dx is equals to minus 2xy square. Now If we shift this term, whole term, left side we can write dy upon dx is equals to minus 2xy square upon 2x square y. Here 2 to cancel. We can write minus x into y square, x into y square. If we get cancel x by y, we can write y upon x, which is dy upon dx. We know that the value of y, x square into y square, if we shift this term, if we multiply this term, x, numerator and denominator, we can write minus x square into y square upon x into x square, which is x cube y. Hence, the value of dy by dx is equals to minus x square y square upon x cube y. We want to prove this minus 1. Here we know that the value of x square into y square is equals to 1. If we substitute number 3, this value x square into y square, which is 1, we can write dy upon dx is equals to minus 1 upon x cube y. If we take this x cube y, left side we can write x cube y into dy upon dx is equals to minus 1. Hence proved, which is a required proof of the given function x square plus y square is equals to t plus 1 by 2, 1 by t, and x raised to the power 4 plus y raised to the power 4 is equals to t square plus 1 by t square. We have proved that x cube y into dy by dx is equals to minus 1. Here the question number 4 is x is equals to a in bracket t minus 1 by t and y is equals to b in bracket t plus 1 by t. Then show that dy by dx is equals to b square x upon a square y. Function is in the form of parametric functions. We have to find dy by dx. By using the definition of parametric function, if we solve this, then we can't get proof, which is b square x upon a square y. Now, first we take both function. We know that x is equals to a into t minus 1 by t and y is equals to b into t plus 1 by 2. Given that x is equals to a into t minus 1 by t and y is equals to b in bracket t plus 1 by t. If we take this a, left side we can write x by a is equals to t minus 1 by t here, and y by b is equals to t plus 1 by t. If we take square x and y, squaring both sides, we can write here x by a whole bracket square is equals to t minus 1 by t bracket square. Again it we can write y by b whole bracket square is equals to t plus 1 by t whole bracket square. Now it is x square upon a square. By using a minus b bracket square, we can write t square minus 2 into t into 1 by t plus 1 upon t square. Again we can write it y square upon d square is equals to t square plus 2t into 1 by t plus 1 upon t square. Here again t cancel, here again t cancel. We can write it x square upon a square is equals to t square minus 2 plus 1 upon t square. Y square upon b square is equals to t square plus 2 plus 1 upon t square. It is equation number 1, it is equation number 2. If we subtract equation 2 from equation 1, now 1 minus 2, we can write x square minus x square upon a square minus y square upon b square is equals to t square minus 2 plus 1 upon t square minus t square plus 2 plus 1 upon t square. Here t square minus 2 plus 1 upon t square it is minus t square minus 2 minus 1 upon t square it is plus t square minus t square cancel plus 1 by t square minus 1 by t square cancel. We can write it minus 2 minus 4 means x square upon a square minus y square upon b square is equals to 4. If we differentiate this function with respect to x, then we can write differentiate with respect to x. We can write 1 upon a square is constant function. We take a derivative of x square minus 1 upon b square is constant function. We take a derivative of y square is equals to derivative of 4, which is constant function, is 0. Now derivative of x square is 2x. We can write 2x upon a square minus here derivative of 2y square is 2y upon b square into dy by dx is equals to 0. If we take this 2y upon b square dy by dx right side, we can write it 2y upon b square into dy upon dx is equals to 2x upon a square. Now if we shift this term right side, then we can write dy upon dx is equals to 2x upon a square into, this term is divided, this term, but we can write interchanging numerator and denominator, we can write b square upon 2y. Here 2 to cancel. We can write b square into x, b square x upon a square into y, a square y, which is a required proof. Dy upon dx is equals to b square x upon a square y, hence proved. So in the question number 5, x is equals to under root of a raised to the power sin inverse t and y is equals to under root of a raised to the power cos inverse t. Here we have to show that dy by dx is equals to minus y by x. First, we take given function, given that here x is equals to under root of a cos inverse, a sin inverse t. If we differentiate with respect to t, we can write dx upon dt is equals to derivative of under root, which is 1 upon 2 under root of a raised to the power sin inverse t, and we take again the derivative of sin inverse t. Again the derivative of a raised to the power sin inverse t. Now we take again derivative of sin inverse t is a raised to the power sin inverse t into log a upon 2 under root of a raised to the power sin inverse t as it is. Here sin inverse t is parameter. We consider that this function is a t. We can write again the derivative of sin inverse t. We know that this under root and this cancel, we remaining there a raised to the power sin inverse t. Also we can write under root of a raised to the power sin inverse t into log a upon 2, and the derivative of sin inverse t is 1 upon under root of 1 minus t square. Now we can write it dx upon dt is equals to under root of a raised to the power sin inverse t, which is a value of x. We can write x log a upon 2 under root of 1 minus t square, equation number first. Similarly, we can find a derivative of dy by dt. Here y is equals to under root of a raised to the power cos inverse t. Equation number 1, 2. Here 3. If we differentiate with respect to t, then we can write dy upon dt is equals to 1 upon 2 under root of a raised to the power cos inverse t, and we take again the derivative of a raised to the power cos inverse t. We know that the derivative of a to the power cos inverse t is a to the power cos inverse t into log a upon 2 under root of a raised to the power cos inverse t as it is, and we take again a derivative of cos inverse t. Here cos inverse t under root cancel, remaining here a to the power cos inverse t. We can write under root of a to the power cos inverse t into log a upon 2, and the derivative of cos inverse t is minus 1 upon under root of 1 minus t square. Under root of a to the power cos inverse t is value of y. We can write it y into log of a upon 2 into under root of 1 minus t square minus sign as it is, which is a value of dy by dx, which gives equation number 4. We can write from 2 and 4 by the definition of parametric function. We can write dy upon dx is equals to dy by dt upon dx by dt. Here dy by dt is minus y log a upon 2 under root of 1 minus t square upon, or we can write it in multiple form by interchanging numerator and denominator. We can write 2 under root of 1 minus t square upon x log a. Here log a cancel. 2 under root of 1 minus t square, 2 under root of 1 minus t square cancel. Implies that we can write the value of dy by dx, which is minus y upon x, which is a required proof. Dy upon dx is equals to minus y by x, hence proved.